Hi everyone, this is Dr.G.Ravindranath Reddy, working as Assistant Professor in MLR Institute of Technology, Hyderabad. So today we are going to discuss how to find out the Fourier series of f of x if that f of x is an even function and odd function in the interval minus pi comma pi. Now in this we will discuss what is meant by even function and what is meant by odd function and what are the formulas we are having to find out the Fourier series of f of x in the interval minus pi comma pi for even function and odd function. So let us take the definition of even and odd function here. So I have taken a function f of x. Now I want to decide whether that function is f of x is a even function or odd function or neither even nor odd. So for this purpose what we are doing is I want to replace that x with minus x in the function here. So you will get f of minus x. If you simplify this f of minus x here, if you get the same function f of x, then we can say that the function is an even function. So that is, so I will take one example here. So f of x is equal to x squared. So in this function I want to replace x with minus x here. So if you replace x with minus x here, so you will get minus x whole square. Once again this is equal to x squared, this is equal to f of x. So even though if you replace x with minus x in the function, if you get that value is once again is f of x, then that function is said to be even function. And suppose if you replace x with minus x in the function, if you get that value is equal to minus f of x, then that function is said to be odd function. For example, if you take f of x is equal to x, so replace x with minus x in the function, so you will get f of minus x is equal to minus x. So minus this x is replaced with f of x. So f of minus x, here you are getting that value is equal to minus f of x, then this function we can call it as an odd function here. Okay. So now even though suppose if you replace x with minus x in the function, we are not getting that f of x value and that value is also not equal to minus f of x, then that function is said to be neither even nor odd. For example, if you take f of x is equal to x squared plus 2x. So now replace x with minus x here. So that is you will get minus x whole square plus 2 into minus x. So you will get this value is equal to x square minus 2x. So this is not equal to f of x and this is also not equal to minus f of x. So in this case, whenever we take this type of function, in this case if you replace x with minus x, that resultant value is not equal to f of x and not equal to minus f of x. So then this type of functions we can consider as neither even nor odd. Now in this video we will see how to find out the Fourier series for even and odd function here. Now let us take the first case here. Suppose whenever the function is an even function. Now let us take the formula to find out the Fourier series for this in the interval minus pi comma pi. So that value is given by that formula. F of x is equal to a naught by 2 plus summation n is equal to 1 to infinity a n cos n x here. So in this standard formula we don't have the bn term here. So bn, so since the function is an even function, this bn value becomes 0. So since bn is equal to 0, we are neglecting that bn term in this standard formula here. So we got only a naught term and an term here. With both these are the standard formula to find out the Fourier series expansion if the function is even function in the interval minus pi comma pi. Now in this we have the standard formula to find out a naught and an. So a naught value is given as 2 by pi integral 0 to pi f of x into dx, and similarly an is equal to 2 by pi integral 0 to pi f of x into cos nx dx. So this is the formula to find out the Fourier series whenever the function is an even function in the interval minus pi comma pi. Now let us take one problem on the even function in the interval minus pi comma pi. Now we will see how to find out the Fourier series for this function, even function. Now I have taken a function f of x is equal to x square. I want to get the Fourier series for this function in the interval minus pi comma pi. That is the first stage of our problem. Now once after getting that Fourier series of that function in the interval minus pi comma pi, by using that Fourier series we have to prove these three conditions here. Okay, now we will complete the first stage. Now we will see how to find out the Fourier series for f of x is equal to x square. Now we will check whether, since the interval is minus pi comma pi, so whenever we want to take the function in the interval minus pi comma pi, first we have to concentrate whether that function is even function or odd function. So just now we have taken the formula. So now we got this f of minus x. If you replace x with minus x here, once again we got f of x. So by using our definition of even function, we can conclude that this f of x is equal to x square is an even function here. So now we have the standard formula to find out the Fourier series of an even function in the interval minus pi comma pi. Now that a naught value, this is the formula to find out the a naught. Now replace that f of x in this function. So f of x is equal to x square. Now we know that integral of x square, we will have that value is equal to x cube by 3. Now substitute the limits, upper limit and lower limit here. So after substituting the upper limit and lower limit, finally we got this value is equal to 2 pi square by 3. You consider this is the value of a naught. Okay, so now let us go for the next coefficient, that is an. So this is the formula to find out the value of an. Follow the same procedure, replace that f of x with x square. So x square cos nx. Now here once if you observe this function inside the integral, we are having the product of two functions, one is x square and the next function is cos nx. Then in this case we have to go for the integral of uv. So integral of uv, this is equal to u into v1. v1 is integral of v minus u dash into v2. v2 is integral of v1 plus u double dash into v3, that is integral of v2, and so on. Okay, follow the same procedure here and get this value. So now u is our x square. Now take x square here, and v1 is nothing but integral of v. Our v is cos. Integral of cos can be written as sin nx by n minus u dash, that is x square, derivative of x square, that is 2x, and next one this is v1, and v2, that is integral of v1, that is minus cos nx by n square. Already here we are having n in the denominator in the v1. So if you apply this integration once again, you will get another n in the denominator. So n into n, you will get n square. Now alternate plus here, and this is our u dash. Now apply the derivative for u dash here. You will get derivative of 2x is 2, that is u double dash, and into v3. So this is v2. So once again apply the integration for v2, you will get this value here. Now simplify this, and by substituting 0, infinity, pi and 0 as upper limit and lower limit, you will get that value is equal to 2 by pi and 0. Since here if you substitute pi here in this, you will get sin n pi. Sin n pi is 0, so we can neglect this. And here minus 2x, replace x with pi, minus into minus plus here, you will get this value is equal to 2 by pi. Now this value becomes 0, minus into minus plus 2 pi, replace x with pi, cos n pi by n square, minus 2 into sin n pi, this also becomes 0. this is the value after substituting the upper limit minus substitute the lower limit here, put x is equal to 0. So, the first term becomes 0. Here if you substitute x is equal to 0, this term also becomes 0. And if you substitute x is equal to 0 in the sine function, this also becomes 0. So, finally, you will get 2 by pi, 2 pi into cos n pi by n square. This is our now. So, 2 into 2, 4, this pi and this pi gets cancelled. So, cos n pi by n square. So, if you want, you can take this cos n pi can be written as minus 1 whole to the power of n. So, we can also take it as 4 into cos n pi, that is minus 1 whole to the power of n by n square. This is the value of an. Now, after finding that a0 and an value, so go to equation 1 and substitute these two values, then we can get our required Fourier series for the function f of x is equal to x square in the interval minus pi comma pi. Okay, this is our. So, whenever we want to prove any deductions by using this Fourier series, you expand this summation here. So if you expand this summation, you will get pi square by 3 minus 4 is a constant. So, we can take that 4 outside this summation and take 1 by 1, n is equal to 1. If you take n is equal to 1, if you substitute in this function, you will get the first term. Take n is equal to 2, you will get the second function, and so on. We can take some values of n and we can get our Fourier series here. Now, by using this Fourier series, we have to deduce the conditions which are given in the problem. Now, we will go for the deductions here. So, now this is our first deduction here. Now, if you want to prove this deduction, this condition, then we have to take the help of this equation 2. Now, in this equation 2, we have to substitute a suitable value of x in order to get our required condition that we have to analyze. So, once if you analyze our Fourier series, what we got, that is second equation, and the condition what we have to prove in all the numerator terms in this condition, here we are having 1, second term also having 1, third term, in all the terms the numerator is equal to 1. Whereas, in equation 2, we are having the numerator as cos x, cos 2x, that is in terms of cos x. So, now what we have to do is, we have to convert this cos 4x, cos 3x, cos 2x and cos x equal to 1. So, for which value of x that cos value is equal to 1, we have to analyze and we have to substitute that x value here. So, in order to convert this cos x, cos 2x, cos 3x, cos 4x is equal to 1, we know that cos 0 is 1. So, that is possible only by taking x is equal to 0. Now, you substitute x is equal to 0 in equation 2. So, if you substitute x is equal to 0 here, in the LHS side, 0 square, that is 0. So, here we got 0. So, pi square by 3, you keep that, we do not have any x term here, minus 4 into cos 0, 1 minus cos 2x, x is equal to 0, here also you will get cos 0, that is 1 by 2 square plus cos 3, 0, cos 0, this is also equal to 1, 1, 1. Now, simplify this. So, if you simplify this, you will get our required condition what we have to prove. So, send this pi square by 3 to this side, then cancel minus and minus, send this 4 to this side, you will get pi square by 12 and this bracket term you will remain here. So, whenever we want to prove any deductions from the Fourier series, this is possible by substituting the suitable value of x in order to get our required deduction here. So, this is our first deduction. Now, we will go for the second one. So, our second condition, this is the condition what we have to prove, 1 by 1 square, 1 by plus 2, 1 by 2 square plus 1 by 3 square plus 1 by 4 square and so on. This value, this series must be equal to pi square by 6. So, for this also, we have to take the help of this second Fourier series, what we got for the given function. And in this function, we have to, once again, we have to substitute the suitable value of x in order to get these values here. So, in the first condition, in order to prove the first condition, we have taken x is equal to 0. We got that cos 0, 1, 1 in the numerator here. Now, once if you observe this one, for the first term, here we are having positive sign, here also we are having positive sign, and for the second term we are having negative sign, here we have to get that negative sign into a positive sign, and like that we have to. So here alternatively plus and minus we are having in our required, we got whatever the series we got here, and here whatever the condition what we have to prove, in all this, in all the terms we are having a positive sign. So in order to get that, I want to substitute x is equal to pi. If you substitute x is equal to pi here, you will get pi square. So pi square is equal to pi square by 3 minus cos pi minus cos 2 pi by 2 square plus cos 3 pi by 3 square minus cos 4 pi by 4 square, and so on. Now we know that we substitute the values here. Cos pi, that is minus 1. Cos 2 pi, we can take that value. So we can use this formula, cos n pi. Cos n pi is equal to minus 1 whole to the power of n. So in place of n, here we are having 2. So minus 1 whole square, that is 1. And here cos 3 pi, you will get minus sign here. So that's why this plus is converted into minus. And cos 4 pi, 4 is a even number. So minus 1 whole to the power of 4, you will get positive sign. So this minus is as it is. Okay. Now simplify this and send these terms to this side. Take minus common here. So here you will get positive sign. And you can send this pi square by 3 to this side. Simplify this and then substitute this, send this 4 to this side, you will get this value here. So 1 plus 1 by 2 square plus 1 by 3 square plus 1 by 4 square and so on. You will get that value is equal to pi square by 6. This is the condition what we have to prove. So this we got by substituting x is equal to pi in the Fourier series of our given function. So now we got two deductions here. Now by using these two deductions, we can prove the third one. The third one is this. So in order to prove this third one, I want to add first condition and second condition and then divide by 2. We can get our required condition here. Okay. So this is the way how we can find out the Fourier series for even function, and by using that Fourier series, we have seen how to reduce the given conditions here. Now we will go for the second case, that is whenever the function f of x is an odd function, then we will see how to find out the Fourier series in the interval minus pi comma pi for an odd function. Let us see what is the formula to find out the Fourier series. So whenever we are having a function, an odd function, so for that odd function, if you want to find out the Fourier series in the interval minus pi comma pi, then by default you will get a naught value is equal to 0 and a n value is equal to 0. So since these two coefficients are equal to 0, then in our Fourier series formula the first two terms become 0. So only the remaining term is our third term. So by neglecting that first and second term in the Fourier series expansion, we got f of x is equal to summation n is equal to 1 to infinity bn into sin nx. This is the standard formula to find out the Fourier series for an odd function in the interval minus pi comma pi. And whereas this coefficient bn is given by 2 by pi integral 0 to pi f of x into sin nx dx. Now let us go for one problem, and by using these standard formulas we will see how to find out the Fourier series for an odd function here. So this is the function he has given, f of x is equal to sin x, and for this function we have to find out the Fourier series in the interval minus pi comma pi. So whenever we get an interval minus pi comma pi, so before going to find out the Fourier series, let us concentrate on the function f of x and check whether the given function is an even function or odd function, neither even nor odd function. Based on this, we can decide the formula to find out the Fourier series. Now we got the function f of x is equal to sin x. Now we know that sin x is an odd function, because so if you replace that f of x with minus x in the function, so you will get sin of minus x. So this is of the form sin of minus theta. So this can be written as minus sin x. So keep minus sign as it is, replace that sin x with f of x. Now the condition is f of x is equal to minus sin x. So this is the condition for odd function. Now we got the given function is an odd function here. Now we have the standard formula to find out the Fourier series for the odd function in the interval minus pi comma pi. So write down that formula. F of x is equal to summation bn sin nx, and by using this standard formula find out the value of that coefficient here. So after finding this coefficient bn value by evaluating this integral, then if we substitute that bn in the Fourier series expansion, then we can get our required Fourier series for an odd function in the interval minus pi comma pi. Now let us see how to find out the bn. Now substitute f of x is equal to sin x sin nx. So we have the formula 2 sin a cos b sin b, 2 sin a sin b. So by using that formula we can find out this, we can convert this in the form of cos of a minus b minus cos of a plus b. Okay, so by using this formula we got this value. So here a is x, b is sin nx. So cos of 1 minus n into x minus cos of 1 plus n into x. Now separately apply the integration for each term. Cos of 1 minus x into integral of cos, we can take it as sin this, and similarly cos of 1 plus n of x, this can be written as sin of 1 plus n into x by 1 plus n. So since the denominator is in the form of 1 minus n, so our n takes the values from 1 to infinity. So whenever we take n is equal to 1, here the denominator becomes 0. So whenever we have this type of situation, while you are finding that a naught value or bn value or an value, then first we have to exclude that n is equal to 1, and by excluding that n equal to 1, we will find out that bn value. After that, let us consider n is equal to 1 and we can find out that b1 value here. So now I am not considering that n equal to 1, so that's why I have taken that n value not equal to 1, because if we then only the denominator is not equal to 0. Now substitute one by one, substitute the upper limit and lower limit here. So if you substitute this upper limit x is equal to pi, this is the value you will get, and when you substitute x is equal to 0 here, you will get sin 0, 0, 0 by anything equal to 0, sin 0, this also becomes 0. So the entire value after substituting the lower limit x is equal to 0, you will get that value is equal to 0. Okay. Now by using this, we will get this value is equal to bn is equal to 0. We have the standard values. So this is bn is equal to 0. This is applicable only when n not equal to 1. Now separately we will take n is equal to 1 and then substitute that in this standard formula of bn. So b1 n equal to 1 is equal to, you will get this value here. So sin x into sin x, you will get sin square x. So convert that sin square x in the form of 1 minus cos 2x. So we have the formula cos 2a is equal to, since we want this sin square value, so you take this cos 2a in terms of sin square. So this can be written as 1 minus 2 sin square a. So by simplifying this, you will get this sin square is equal to 1 minus cos 2x by 2, and find out that integral. So this 2 and this 2 gets cancelled. So the remaining one is 1 by pi, integral 0 to pi 1 minus cos 2x dx. So now separately apply the integration. So integral of 1, we can take it as x. Integral of cos 2x, that can be written as sin 2x by 2. Now substitute the upper limit and lower limit in place of x. So if you substitute upper limit and lower limit here, you will get that value is equal to 1. So whenever we take n is equal to 1, we got b1 is equal to 1. For the remaining values of n, we got bn is equal to 0. So substitute that Fourier series. So neglect that n value which is greater than 1. So that becomes 0. Now we will get only 1, that is b1 into sin x, that is sin x. So this is the Fourier series of our required function. So now in this video we have seen how to find out the Fourier series expansion for f of x whenever that f of x is an even function or odd function in the interval minus pi comma pi. So now in the next video we are going to discuss how to find out the Fourier series expansion for the discontinuous functions in the interval 0 comma 2 pi and in the interval minus pi comma pi. Thank you all.